Now in this section we're going to talk briefly about correlation analysis. This is a very short section, and so this is going to be a short lecture video. So suppose we have a bivariate random sample of size n from a normal distribution where rho is the population correlation between x and y. Now from the sample we can calculate a sample correlation, and we need to distinguish between the sample correlation and the population correlation, and so we'll use lowercase r to denote the sample correlation. Then it can be shown that the random variable given by this expression here on the in the middle of slide 2, r times the square root of n minus 2 all over the square root of 1 minus r squared, has a t-distribution with n minus 2 degrees of freedom. Now this can be used as a basis for developing inference procedures about rho, such as performing hypothesis tests about rho and constructing confidence interval estimates for rho. Now one approach at constructing confidence intervals for rho is called Fisher's approximation, and it's performed in the following way. In order to construct a 1 minus alpha times 100% confidence interval estimate of rho, we use the formulation given here. All right, so this quantity is that I'm highlighting is the lower end point of the interval, and this is the upper end point of the interval. And notice that this is quite a complicated set of formulas for constructing the lower and upper endpoints. Much more complicated than it is than we would use for constructing confidence intervals in a first methods class or two. These lower and upper endpoints involve the inverse hyperbolic tangent function and the hyperbolic tangent function. So the inverse hyperbolic tangent function is given in the middle of slide 3. And you can see here that it involves the natural log function. All right, so just want to point out to you that in my notes, when you see log log, okay, that is the natural log function. And then the hyperbolic tangent function is given by this expression at the bottom of slide 3. Now, another method, which is based on a better approximation. Both of these methods that we're talking about, both Fisher's approximation on slide 3 and then the method on slide 4 are based on approximations. Rubin's is evidently based on a better approximation, and we're not going to go into the details for this calculation, but if you want to see that, you might look on page 38 of Dallas Johnson's text. But there are several methods for constructing confidence intervals for a population correlation coefficient. There are other methods as well. For example, we might use bootstrapping or something like that. I guess one question I might pose to you is, what if you wanted to construct confidence intervals for differences of correlations? For example, in a first methods course, you look at how to construct confidence intervals for population proportions. And then a little bit later on in the course, you see how to construct confidence intervals for differences of proportions. What if you wanted to compare two correlation coefficients and you wanted to compare them through their difference? Can you think of ways to do that? Now, one of the reasons I wanted to talk about correlation analysis at this point in the course is in large part due to what we're talking about here on slide 5. So in a multivariate setting, which we're going to be in this course, we must exercise caution when interpreting the significance test for correlation coefficients. What we're going to find is that if we use, for example, proc-core in SAS, that it's going to perform a lot of hypothesis tests for us. For every correlation coefficient that exists between variables, it's going to do a test. And the number of possible correlations, the number of correlation coefficients is going to get large pretty quickly as the number of response variables in our data set increases. So when you have p response variables, the number of correlations, and remember what we're looking at here are pairs of variables, pairs of response variables, and for every pair there's going to be a covariance and there's going to be a correlation. And the number of such correlations as a function of p is going to be p times p minus 1 over 2. So the number of correlations grows quadratically with p. And so when you have a large number of response variables, when p is large, then there are going to be lots of correlations, and therefore there are going to be lots of opportunities for type 1 errors when testing the significance of them all using separate tests. And Proc Core and SAS, when it's testing these hypotheses about the population correlation coefficients, those are all separate individual tests. And so, for example, what if you had 15 response variables? Now, that's not at all uncommon. It's not unusual at all for a researcher to have 10, 15, 20, or even more response variables in a given data set. If you have 15 response variables, then there are 105 correlations. All right? There are 105 pairs of response variables, and for each pair there's a correlation coefficient. So you can think of the output from Proc Core. Proc Core is what we use in SAS to do a correlation analysis. And so it's going to do 105 hypothesis tests involving correlations. For each possible correlation, it's going to perform, by default, it will perform the null or test where the null hypothesis is that the correlation coefficient is 0 against the alternative hypothesis that the correlation coefficient is not 0. And for 15 response variables, there are going to be 105 hypothesis tests that it's going to be performing. And so there will be 105 opportunities, okay, 105 opportunities for type 1 errors. Now, if each one of those tests is done at the significance level of 5%, then even if no pair of variables are correlated, you would expect to see about 5 significant correlations, 5 significant tests in that collection of 105 tests. So we've got to be very careful when we interpret the results from a program or an analysis produced by something like Proc Core, because it's very easy to get led astray if we're not careful. Now, one approach to controlling the overall type 1 error rate, and that's what we're talking about here, is trying to make inferences while at the same time maintaining control over the type 1 error rate, the overall type 1 error rate. One way to do that in this context would be to perhaps perform a Bonferroni adjustment. So instead of performing each of these 105 tests at the 5% significance level, perform each one at a significance level equal to 0.05 divided by 105, where you could ballpark it and perform each one at a significance level of 0.05 divided by 100, which would be 0.0005. And if you do that, then you're going to ensure that your overall type 1 error rate for that suite of tests is going to be no more than about 5%. So you would be, in fact, controlling the overall type 1 error rate. But the Bonferroni approach, as you probably know, is very drastic. It really, really diminishes your power. And so you may miss some significant correlations by using that approach. Now, if you think back to analysis of variance, your first and second methods classes where you covered analysis of variance, and even in your first methods class, you looked at performing multiple comparisons. So let's think in our minds about analysis of variance. And we're going to, in analysis of variance, what you're doing is comparing the means of multiple populations. And if the overall ANOVA is significant, then what you're going to conclude in that situation is that at least one of the means is different than the others. And so then quite often, what you want to do is to perform pairwise comparisons to see where the differences are. And one of the approaches in that type of situation to control the overall type 1 error rate is to perhaps do a Bonferroni adjustment or Tukey's adjustment, something like that. But another approach is to decide beforehand that you're not going to look at pairwise comparisons unless the initial ANOVA is significant. And that's typically called the Fisher's protected LSD. And so what you would do is, as a matter of practice, in doing that kind of a test, what you would do is you would perform your ANOVA. And if it's not significant, then you would stop. You would go no further. You would not drill down and do pairwise comparisons. On the other hand, if you, and by the way, you would do that ANOVA, that overarching ANOVA at, let's say, a 5% significance level. And so if if the overall ANOVA was not significant, then you would stop, you would not drill down. If it is significant, then what you would do is you would do the pre-planned pairwise comparisons that you had in mind before you started the analyses. And then and you do each of those at the 5% level. Now, if you do that, and if you're strict about it, then your overall type 1 error rate is in fact 5%. And so when you think of it that way, the overarching ANOVA, we can think of that as a gatekeeper test. We're not going to proceed through the gate. We're not going to proceed and drill down and do pairwise comparisons unless that overall ANOVA is significant. Now, in the same way, in this context, when we are wanting to make inferences about the correlations between our response variables, we need to have some way of managing and controlling the overall type 1 error rate. And again, one approach that I had talked about a few minutes ago was using a Bonferroni adjustment. All right, so for example, in this case, instead of performing each of the correlation tests at the 5% significance level, do each of the tests at a significance level equal to 0.05 divided by the number of tests. And so that would be about 0.05 divided by 100 approximately. But like I said, that can really diminish your power. And remember that when we're performing hypothesis tests, we want to have as much power as possible. We want to have as much power as possible while still maintaining control over our type 1 error rate. So there's a balancing act, all right, and we have to make sure that we don't diminish our power too much. You know, if there are better alternatives, better ways, more effective ways of managing that overall type 1 error rate while still maintaining power, then obviously we would want to use that approach. And so in a manner analogous to the Fisher's protected LSD in the context of analysis of variance, what we might want to do is think about, is there some way that we can perform one overarching omnibus test for all 105 correlations at once? You know, that serves as a gatekeeper test. And then if that null hypothesis for that gatekeeper test, and that null hypothesis would be that all 105 correlations are 0, the alternative would be the opposite of that. It would be that at least one of the correlations is non-zero. And so if we had such a test, and if we held strictly to the process or procedure where we did not look at the individual tests unless the overall test was significant, then we would again have a procedure where the overall type 1 error rate was maintained at, let's say, 5%. So we want to keep that in mind as we go forward, and we want to see if there's some procedure that we can use to serve as a gatekeeper test when testing hypotheses about correlations. So that's all we're going to say right now about correlation analysis. I may make another video and show you some examples using PROC-Core, examples of correlation analysis that actually demonstrate, for example, Fisher's approximation. This is built in. I showed you this formula so that you know what it is, but the good thing is that, well, in most cases, when we're analyzing data with software, we're not going to have to do this. Okay, SAS has already implemented this in the procedure, in the correlation procedure, and so all we have to do is ask for it. So I will show you how to do that in a subsequent video, and so that's all for now. So I'll see you in the next video.